Welcome to the Big Fun Lectures. First off, here we've got a program with some question marks and the types. What type gets inferred for those question marks? We have the identity function, which is question mark to question mark, and that's equal to a function that returns its input. Then we apply identity to the number 10. Well, since 10 is an int, the type that gets inferred is int. Now, what if we apply ident to a different argument? Here we're applying it to a function. This function takes in an int named y and returns y. What type do we infer here for the question marks? Int arrow int. So overall, ident is a function that takes in an int arrow int and then returns another int arrow int. Now what if we have a program that applies ident to both of those arguments? Here we've got an if expression, and we've hidden the condition for now, because the point is that in these two branches, we apply ident to two different arguments. In the first branch applied to 10, and the second branch applied to our function that takes in a y. And then since we know that this call to ident with the function will return another function that takes in an int and returns an int, we apply that function to the int 8 to make sure that both branches have the same int type. So what should go in the question marks? Clearly something should be able to go in there because we were able to do both of these calls by themselves. But with our current mode type system, we run into a problem. There's no one type that we can write in here at the moment to make this work out. This should type check though, and so that means it's time to grow our type system. We'll need to add a new kind of type to the language to express polymorphism. And if you're familiar with generics or other kinds of type abstractions, that's the idea that we're going to follow here. Let's take a look. As a first draft, we're going to change the way that we write the code for identity. Before, ident was this little fun that abstracted over a value. Now we want to wrap that little fun in a big fun, and this one abstracts over a type. Hence the question mark A here, saying that we're expecting a type argument. Then down below, when we go to apply ident, make sure to supply a type for both of the applications. With ident of 10, we supply type int. With ident of a function, we supply the type int arrow int. Putting it all together, the ident function is now polymorphic because we've wrapped the little fun with a big fun form, and that parameterizes over a type. We can substitute any type in for the argument, and we'll do that using those square brackets like you see down below. That gives us polymorphic expressions. Now it's time for polymorphic types. What is the type of this big fun? Well, it should be something like alpha arrow alpha, but before we can actually call this function on a value, we need to supply a type first. So we don't exactly want alpha arrow alpha. We'll want to wrap that type in something else that says we're quantifying over a variable, alpha. And also, whatever type we end up choosing, we'll want to make sure that we can distinguish that type from the type for this expression here, where we have two layers of big fun. Since those big funs have the same little function on the inside, the type for this expression should be something like alpha arrow alpha. But once we've picked a type for alpha, we need to pick a second type for that beta before we can go ahead and apply the function to an argument value. With that in mind, we will introduce a new type form called for all. For all takes in a symbol for a type variable and then has a type inside for its body. And here are two examples. The for all for the expression on the previous slide will look like this. For all alpha, we have alpha arrow alpha. And the type for the expression up above is for all alpha, for all beta, alpha arrow alpha. To summarize, here's the grammar that we'll use for polymorphism. We've got 4 new additions. First, at the expression level, we have big fun for a function that abstracts over a type. And then we have square brackets for a type application. Down below, we extend our types. A for all type takes in a symbol and then has a type as its body. And this means that we have one more extension. Symbols need to appear inside of a type. And that's because when we write for all alpha, alpha arrow alpha, we will get down to an arrow type in the body. And then on the left and right of that arrow, we'll have symbols. So we'll need to allow those symbols in our grammar for types.